Hi students, the laboratory today will be a strain measurement. Firstly, I'm going to show you about the introduction of a theory that concerns to the laboratory. There are two parts. The first part will be for the actually electronic stuff, with some circuit you need to use for the measurements. And the second part will be for the mechanical problem and then how we find the strain for the measurement. So the first theory we call the Wheatstone bridge. So I expect you have learned this Wheatstone bridge in the electronics, so some course you've done in electrical engineering. This circuit used to amplify the signal. The things about the strain you have learned, the strain is something with small things, and then they give you a very small output for the deformation of any material that you put the strain gauge on. So if you have the low output, you need to amplify the signal. And this kind of circuit helps you to amplify or enlarge the signal. So I give you the concept. It's just like this. So, this is the resistance, like what you have learned. This is the voltage or the input voltage for the circuit. This kind of circuit we call the Wheatstone bridge circuit. You see the theory. If you would like to find the potential or the voltage of EA, it means among A and this point, EA will be R3 R1 plus R3 times E. This is the voltage or the input voltage. The output between A and this point will be EA with this circuit. And then for EB, supposed to be almost the same thing. 4 plus 2 plus R4 times E. Then what happens? If you would like to find this is the input to the system, it's just like DC input. And this is the output between A and B. That's so-called EAB equal to EA minus EB. So what we have, if you look at this, you have E bracket, 3, 1 plus 3, minus 4, 2 plus 4. So what does it mean? If your system is balanced means R1 over R3 equal to R2 over R4. If it's balanced, you can see that the output voltage will be 0 exactly. So if the system is balanced, I say the ratio of the resistance is balanced, the output voltage will be 0. And what happens if this is my strain gauge example? The strain gauge used to measure the output from the deformation of the material. Let's say if my material is deformed, the resistance is changed. If the resistance is changed, the ratio here is changed, and my output voltage here is not going to be 0 anymore. So it's supposed to be some value. So that value we could relate that to the strain and the output voltage. It could be some relationship between each other. So what does it mean? If I put the strain gauge to measure any deformation of any system, if it starts deforming, resistance will change. Why is it changing? Resistance depends on the length. It depends on the diameter of the wire that you're learning solid mechanics. If this one is changed, the ratio is changed. The system is not balanced. Then the output voltage is not 0. So we take this output voltage to be in relation with the input voltage here and relation with the deformation of the system. So later on, if you look at the measurement, we could find the output voltage here from the experiment. And the output voltage here will link to the deformation of the system. And I'll show you later. Now, the second part is for the mechanics. Let's see. For the mechanics, what you have learned about the strain. So obviously, we have learned the Young modulus equal to normal stress, normal strain. That's what you have learned. The Young modulus equal to normal stress over normal strain. What is the normal stress? We supposed to get normal stress from bending. The bending is one of our measurement today or the experiment today. So I have a beam and I'm going to bend it to show you about how we use the strain gauge to measure the deformations. So if we talked about the bending, normal stress equal to MC over I. What is it? M is a moment, C is a distance from the neutral line to the point you find the normal stress. I, it's a moment of inertia. If the cross section is rectangle, this is B, this is H. I equal to 1 over 12 BH cubed. Again, C is a distance. If the neutral line is here, okay, say it's a start from the neutral line to any point, so mostly the maximum normal stress will be on the top, on the bottom, what you have learned in statics or solid mechanics. And what about the moment? I will show you later. The moment, force times distance. If you got normal stress, you could find normal strain equal to normal stress times the Young modulus. If you could find normal stress, if you could find the Young modulus, you could find the strain. Now, later on, you see that you could calculate the normal strain. This is from calculation. And then we're supposed to compare it with the experiment. That's from you got from the output voltage, and then you change it to be normal strain. So, and then we are going to compare between normal strain from experiment and normal strain from calculation. So let's see the second part. Okay. Okay, let's see the experimental set we have to do for today. I have the box here, I call it the amplifier. The box here, I'm going to explain later. And I have a small box on my left side here. This is a Wheatstone bridge. You could see the circuit here. This is a Wheatstone bridge. And then you could see a cable here, a wire here. It's moving to the strain gauge here. See, this is the strain gauge. You could see closely, you see, this is a strain gauge. We glued it on the cantilever beam. So this is a part of the one resistance. I said that it's vary with the deformation of my cantilever beam. And this is a mass. Okay, this is a mass. I'm going to hang the mass here, like this. Because when I hang the mass here, you see, from a whole system, I create a moment to the cantilever beam. When I create a moment to the cantilever beam, so I have the normal stress here. So if I have the normal stress, I could find the normal strain. That's what I previously explained about it. Now, let's see. If you see in detail of the box here, you see, this is the amplifier. This is the output voltage. Now you could see that this is the output voltage. Now you could see that it's not zero. Actually, it's supposed to be zero if you could set it or make a zero set to the system. But now let's say your initial output voltage could start from minus 0.15. Let's say minus 0.15 as your reference. Just think about this is a 0 or your reference. So this is all the set. So what we put the assumptions here. We put the assumptions here. A 2 volt equal to 250 micro normal strain. This is the setup from the box. I'm going to explain it on the board here. Now, let's say the cantilever beam I show you, we have a cross section. The width 5.5 centimeter, the height 0.3 centimeter. Now, if you look at the cross section of the beam, this is a cross section of the beam, my cantilever beam, the width and the height. And as I said, we assume from the box, amplifier box, 2 volts to output voltage equal to 250 micro strain. Micro, it is 250 times 10 power minus 6 normal strain. Don't forget, micro strain, 250 times 10 power minus 6 normal strain. Now, you see the experiment. This is my cantilever beam, you see. Exactly. I have the mass here, like I said, I'm going to put the mass here. I have the strain gauge here. So what happened? I have the Young modulus of the cantilever beam, 210 gigapascal. 210 gigapascal. So what happened? If you would like to find the normal stress, now I show you. If you would like to find the normal stress, like I said, MC over I, isn't it? What is M? M is a moment. How did you find a moment? You said you have the mass hanging at the end of the cantilever beam. It's mg. The distance, I did measure the distance for you, 102 millimeter. So what is my moment? Mg. Isn't it? So let's use the lowercase m. So mg times 102 10 minus 3. So my moment, living moment, depends on the mass. Okay, it depends on the mass I hang it on. So if I got the bending moment, I'm going to substitute it in. And what does it say? As you know, what is the height? The height is 0.3, isn't it? So my C, the maximum normal stress always happen at the top or the bottom of the surface. So my C is supposed to be 0.15 10 minus 2. Because half of the thickness. Start from the neutral axis to the top or to the bottom is a half of the distance. What is I? I 1 over 12 B H Q. What is B? The width. 5.5 centimeter. What is the height? 0.3 centimeter. That's it. That is the normal stress you could find. And how did you find normal strain? From calculation. Normal strain equal to normal stress over Young modulus. Could you find normal stress? Yes. Do you know Young modulus? Yes. 210 gigapascal. So you could calculate for the normal strain. Now, this is the normal strain from the calculation. Now let's say that